So today is 20th of October. It is an afternoon, the first day of myself transacting the lesson P block elements with you all. It is chapter 11 of your class 11 syllabus. Okay. Now, what are P block elements? How do you identify the P block elements in the periodic table? Now, for that, understanding that, have a look at your screen now. If you look at the screen very carefully, on your screen you will see that elements which are belonging to group 13, 14, 15, 16, 17 and 18. This block has been given a name as P block elements. Okay, so boron, aluminum, gallium, indium, thallium, and carbon, silicon, germanium, tin, and lead. Out of all these P block elements in your class 11 syllabus, we are advised, we are told to study thoroughly with respect to the syllabus only group 13 and group 14 elements in detail. Okay, so now moving to the next part of the chapter, the introduction part of the chapter, unit 11, some P block elements on your screen. Now we know already, I've already told you that what you call this, what you call elements belonging to group 13, 14, 15 and 16 and 17 and 18 also constitute a separate block in the periodic table. In these elements, the differentiating electrons enter the p subshell of the outermost shell. Therefore, the block is called the p block. And these elements are referred to as p block elements. Now, the position of p block elements is shown over here. Okay, these are the p block elements, but you don't have to study 15, 16, 17, 18 in class 11. Only on 13 and 14 in detail. That's why the heading of the chapter is some P block elements. Please keep that very, very clear. Don't say that you have to learn the entire P block. No, it's not like that. Only two groups. Now, coming below, P block elements are known as normal or representative elements. Okay, so let us try to understand the general trends in chemistry, the periodicity of P block elements. Okay, now let us first move to the first one. The first property, that is called electronic configuration. Except helium, the valence shell electronic configuration of P block elements, it is following this order: Ns2, Np, 1 to 6 electrons. This is the valence shell electronic configuration. It is Ns, this is 2 electrons completely filled, and Np, the p orbital, can have 1 electrons to 6 electrons in them. So this is the general electronic configuration of the P block elements in the valence shell. Moreover, the inner core electronic configuration may differ. It may differ. The physical and chemical properties of these elements are considerably affected by the difference in the electronic configuration of inner core. So basically, you have to remember that the chemical properties as well as the physical properties depend upon the electronic configuration of these elements of the P block, depending upon the electrons present in the inner orbitals. There are inner orbitals also. Okay, so the number of inner orbitals, the number of electrons in the inner orbitals. Okay, the availability of whether d orbitals is there or not. Okay, in the inner orbitals, they tell us whether the physical or the chemical properties will differ, or accordingly they will react with some other compounds in chemistry. Now, after the electronic configuration, moving down to the oxidation state. The maximum oxidation state exhibited by a p block element is equal to what? Is equal to the sum of the ns and np electrons. So here, to get the oxidation state, if there are 2 electrons here in the s orbital and there is 1 electron in the p orbital, then the oxidation state becomes +3. That means we have to add over here 2 plus 1, that comes to +3. So that is the what you call oxidation state exhibited by a p block element. Okay, that is the total number of valence electrons. On account of this, the number of possible oxidation states increases as one moves from left to right in the p block. In addition to the group oxidation state, the P block elements may also exhibit other oxidation states as well. They can show a variety, more than one oxidation state, which is visible in this table over here, table 11.1 in your textbooks on page number 638. If you look at this table very carefully, group 13 elements, their general electronic configuration is showing NH2 and P1. The group oxidation state, it is generally +1, but other oxidation state exhibited by some of the elements of the group is also +1. At the same time, if you look at group 14, group number 14, the general electronic configuration of the valence shell, it is NH2 and P2. So 2 plus 2 is giving 4. So the group oxidation state is +4. The oxidation states, other oxidation states shown by this group 14 elements, it is either -4 and +2. So here you can see these all are just for comparative purpose. This is not required for us. Okay. Now, after that, coming down to a very inert, very important effect, which is called inert pair effect. Mind it. Don't say that I have not heard this word before. Today, let me explain you. Inert pair effect. Now, inert pair effect means what? Unwillingness. Unwillingness of the electrons present in the inner orbital to participate in bonding. That is called inert pair effect. Are you getting it? So I am repeating once more. Inert pair effect means the unwillingness of the electrons present in the inner orbitals to participate in bonding. To participate in bonding. Okay? Am I clear? I repeat once more. Inert pair effect, it is
Yes,
the reluctance. It is the reluctance of the electrons, unwillingness to participate in bond formation, whatever bond it is forming. Okay, now here on the basis of this very super simple definition of inert pair effect, let us look at this paragraph over here. In group 13 elements, boron family, group 14 and group 15 nitrogen family, the group oxygen state is most stable state for the lighter elements in the group. However, if you move down for the heavy elements in the group, the oxygen state 2 unit less than the group oxidation number. So if you look over here, +4, this is becoming +2. If it is +5, +3 and -3, +6, -2 is +4, +7, +5, +8, +6. So it is 2 less. Now, the inner orbital electrons, they are what? They are not willing to get lost from there and participate in bond formation. Okay. Now, after that, now why does this happen? Let us see. This is basically due to the inert pair effect. For example, in group 15, let us try to understand this properly. Let's try to understand this properly over here. Uh, in group 15, the stability of the group oxygen state is +5. State decreases while that of +3 oxygen state increases on moving from top to. That means in group 15, if you look at group 15 elements, nitrogen, phosphorus, arsenic, antimony, bismuth, group 5 oxidation state is +5. But when you move down, +3 becomes more stable. +3 becomes more stable. That means group 5 elements are most easily found, most conveniently found in their compounds existing in the +3 oxidation state. Moreover, the inert pair effect involves the reluctance, it means unwillingness of NH2 electron pair to get excited and to take part in bond formation. So the definition is there about inert pair effect. In other words, we can say the NH2 electron pair becomes increasingly inert as one moves down a group, resulting in a decrease in the stability of the group oxidation state. So that is inert pair effect. That is the next property. Now after that, moving to the next, that is number 4, chemical behavior. General chemical behavior. Okay. Now here it is quite interesting otherwise to note that the non-metals and metalloids exist only in the p block of the periodic table. Please note that the non-metals at the same time non-metal what you call metalloids exist where you will find these two class of elements only in the p block. You will not find them anywhere else. The non-metallic character of the elements decreasing on moving down the group in the p block, and the heaviest element in each group is most metallic in nature. So remember, the element of the p block which is heaviest it is bound to be metallic in nature. Okay. Therefore, the gradual change from non-metallic to metallic character affects considerably the chemistry of elements placed in a particular group. Non-metals usually possess higher IP. We know that. They need lot of energy to remove the electrons from the valence. That means we can talk about non-metals possessing higher ionization potential or higher electronegativities than the metals. Therefore, non-metals form anions. They form anions. In contrast to the behavior of metals, readily forms cations. The compounds formed by highly reactive nonmetals with highly reactive metals are generally ionic due to the large difference in what electronegativity values. But if you look on the other hand, compounds formed between nonmetals are usually covalent in nature due to small difference in the electronegativities. The oxides of nonmetals are acidic or they may be neutral, whereas those of metals are basic in nature. Now, in any group, you look at, the first element is always behaving quite differently from the other members. That's why we have a word which is called anomalous behavior of the first element of the group. The first element of each group you're talking about over here in P block shows an anomalous behavior and differs from the other elements of the group in several properties because of these following reasons, like small size of the element, high ionization enthalpy of the element, high electronegativity of the element, and then most importantly, number 4, that is absence of vacant d orbitals or orbitals in the valence shell. That means there are no d orbitals at all. That's why, because of all these 4 factors, the first element of any group, it is what? It behaves anomously. The first element of each group is the smallest in size as compared to all these other elements of the group. Several properties of elements depend upon the size of the atoms. Moreover, the first element of each group possesses much higher values of IP and electronegativity as compared to the other elements. These properties also influence the physical and chemical behavior of the first element. This is why the first element of each group differs from the other elements of the group in several properties. Now, moreover, here, if you see these things, an important factor responsible for the unique property of the element is absence of d orbitals. I've already told you. So this part we will not go through. Rather, we'll move to the next property over here. Next topic over here. Under group 13 elements, the more important thing is uh, the boron family, which is called group 13. That is boron family. Here, the elements belong to the boron family are aluminum, boron, aluminum, gallium, indium, thallium. These elements belong to the P block, okay, and as I've already told you, they obey a general outer electronic configuration ns2, ns1 to 6 electrons in their valence shell electronic configuration, okay. Now, except aluminum, the other elements of this group are not much abundant in nature, but aluminum is highly abundant in nature. That's why we get a lot of aluminum utensils and all. Indium and thallium occur only in traces. In the Earth's crust, boron and gallium are rare. However, aluminum occurs in large quantities in Earth's crust. This aluminum is the third most abundant element occurring in the Earth's crust after oxygen and silicon. So, you can imagine, aluminum is the third most abundant element where? In the Earth's crust, just after oxygen and silicon. After that, occurrence of the group 13 elements. Boron, the first member of the group, does not occur in free state in nature, but in the combined state it occurs in the form of boric salts of boric acid. Okay. Aluminum is the third most abundant element, 8.3% by weight. That is quite huge. In the Earth's crust after oxygen. Oxygen is 46% and silicon is 27.7. So oxygen, silicon, then comes aluminum. The most important ore of aluminum we know, we've learned in class 10 also, it is bauxite Al2O3.XH2O. Okay. Now coming to the article over here, the electronic configuration of elements of group 13. Look at the electronic configuration. Okay. General characteristics, under the heading general characteristics, important characteristics are given below. Now here, in this element, the differentiating electrons enter the NP subshell. They possess electronic configuration of the type NH2 NP1 because it is group 13. 2 plus 1 is 3. 3 plus 10 gives 13. Thus, they have the 3 electrons in the valence shell, 2 in s orbital and 1 in always in the p orbital. The electronic configuration is shown over here. So, I request you all to practice writing this electronic configuration by following the Hund's rule of maximum multiplicity, the Polish exclusion principle, and the Auburn's rule. Okay, so you should be thorough. You should be able to write once you get the atomic numbers. Immediately, you should be able to write down the electronic configuration in this form and in this brief representation also. Now, after that, physical properties of group 13 elements. This table is given over here. Table 11.3, that is for comparative purpose with respect to atomic number, mass number, radius, ionic radius, okay, density, melting point, boiling point, whose explanation why is the variation so will this explanation will learn in this over here, physical properties. The atomic and ionic radii of group 13 elements are smaller than those of the corresponding elements of group 12. Smaller, why? Because of the increasing nuclear charge. Effective nuclear charge is becoming higher. So you please read through this. It is very easy, not so difficult. Then in general, the atomic and ionic radii of group 13 elements increase on moving down the group. The reason is given over here. This is because introduction of a new electron shell in at each succeeding element on moving down the group. The increase in the nuclear charge is compensated by whom? By the screening effect of the inner electrons. This is why the atomic and ionic radii in general increase on moving down the group. Okay, so there is one word over here which is called screening effect. The electrons present in the inner orbital, they screen the effect of the nucleus, which is holding the outermost electrons toward itself. That's why this effect, this is called screening effect. Now, after that, there is a question over here which has been asked. The atomic radius of gallium 135 picometer is slightly lower than that of aluminum 143, though gallium is below aluminum. This is because of a very important phenomena happening over here. The atomic radius of gallium should be more than that of aluminum, but it is not like this. If you see aluminum, it is more, 143 picometer, whereas gallium is lesser, 135 picometer. Now, here the explanation is mentioned over here. Because of the differentiating electrons entering into the d orbitals, the screening effect of the d orbitals is imperfect due to their peculiar shapes and poor penetration power. Thus, the d orbitals present in gallium are unable to screen the nucleus effectively. So, they cannot screen because d orbitals are poorer in screening, poorer in blocking the effect of the nucleus on the outermost electrons. Okay, that is why in case of gallium, the outermost electron, the valence electrons held strongly by the nucleus, that make the size of the gallium atoms of the ion smaller. Okay, so that you read over here carefully. Now, with regard to density, densities of group 13 elements are higher comparatively to those of 12 elements, group 2 elements. Okay, so reasoning is given over here. Why? Because it is less closely packed in the lattice, crystal lattice. Melting and boiling points. The melting and boiling points of 13 elements also higher. Okay, because of increasing attraction of electrons between the atoms in the solid state as well in the liquid state. Okay, then ionization enthalpy also. The ionization enthalpy values of group 13 elements exhibit the following trends. So please underline this trend over here. The first ionization enthalpy of group 13 elements are lower than those of the corresponding elements of group 2. The reason is important. If you look at the reason, the valence shell electronic configuration follows this type NH2 and P1, while those of group 2 elements are NH2 only. Obviously, the first ionization enthalpy of group 13 elements will be the energy involved in the removal of NP1 electron, while that of a group 2 element will be that removal of a NS2 electron. Since an s orbital is more penetrating, s orbital penetrates more towards the nucleus, that means it is attracted more by the nucleus than the p orbital. The energy required for the removal of an s electron is higher, okay, than that of needed for the removal of a p electron. That is why you can say the first ionization enthalpy of group 13 elements are lower than those of the corresponding elements of group 2. So here there is an anomaly over here. But if you look at the second and third ionization enthalpies of group 13 elements are much higher as compared to the first ionization enthalpies. So here there is no such effect. Penetration effect is not quite distinct in the case of the second and the first, third ionization enthalpies. Okay. Then number C, on moving down the group, the first ionization enthalpy of 13 elements decreases. It becomes less and less. That you can remove electrons much easily because of bigger size of the atom or the ion. Okay. Therefore, we can say gallium and aluminum exhibit a slight increase in the first ionization enthalpy. So that much will be sufficient from here. Then going to the next column over here, that is electronegativity. The elements of group 13 are more electronegative than those of group 1 and 2. The electronegativity first decreases from boron to aluminum, and then when you move down, when you move further, increases on moving down the group. Reasoning is here, that is important. The higher electronegativities of group 30 elements as compared to those of 1 and 2 may be attributed because of the smaller atomic sizes. The increase in electronegativity is due to the discrepancies in the atomic size of element, because atomic sizes are changing. It is changing. Okay. If you compare with group 1 and 2, atomic sizes of group 13 elements are lesser. So that's why that is how the electronegativities are higher. Okay. Then the electropositive character, the metallic character we're talking about. The elements of group 13 are less electropositive than the corresponding elements of group 1 and 2. Explanation: this is due to smaller atomic size, radii, and higher IP. Okay. So here if you see on moving down the group, the electropositive character first increases from boron to aluminum and then decreases from aluminum to thallium. Boron is semi-metallic, behaves more as a non-metal. The other elements of the group are metals, generally metallic in nature. Okay, so this trend you must try to remember. Okay, then moving to the oxidation states. Oxidation states over here. As the elements of group 13 have electronic configuration NH2 and P1, their group oxidation state is +3. It is +3. They are expected to exist both in +3 and +1 oxidation state in the compounds. The first two elements of the group, that is boron and aluminum, exhibit only +3 oxidation state, while the other elements will show even +1 oxidation state. The stability of +3 oxidation state decreases while that of +1 oxidation increases on moving down the group. Okay, so here this is because of inert pair effect. So this reluctance of the electrons in the inner orbital to participate in bonding by getting themselves lost from the orbital, it is called inert effect. Oh, that's why the reluctance of the valence shell s electron pair to get unpaired and to participate in bond formation is generally called inert pair effect. So remember, the inert pair effect becomes more pronounced on moving down the group. This is due to the progressive increase in the nuclear power, nuclear charge experienced by the NS2 electrons due to the ineffective shielding of the nuclear charge by inner d and f orbitals. Okay, so this you read through carefully. Then coming to the reducing properties, reducing character, we are doing the general introduction to the group 13 elements. Now the reducing power of group 13 elements is lower, that much only you remember, than that of group 1 and 2. Explanation you may not go through, you may leave it out. Nature of compounds. Boron, the first member of group 13, forms a covalent compounds. In fact, boron is unable to form ionic compounds containing B+3 ions. This is because the first three ionization energies of boron are much higher than the corresponding values of the remaining electrons of that. So that much only you remember. Okay, boron forms covalent compounds. Okay, then if you look at after that, coming to down to the chemical properties of these elements on page number 642, chemical properties of 13 elements. Here you try to go through these reactions, action of air and water. Okay, this reaction, action of air and water on this element, like boron reacts with oxygen from boron oxide. Okay, with nitrogen also it reacts from boron nitrate. Then after that, aluminium with water, that is steam, it forms aluminum oxide. These elements also formed what you call the elements of group 13 do not combine directly with hydrogen. However, a number of hydrides of these elements have been obtained by indirect methods, which have been discussed over here. Okay, so we can see hydrides of other members of the group 13 The other elements of the group 13 form only few stable hydrates and they are polymeric in nature. Okay, they form polymers. Whereas if you talk about hydrates of boron, which are more important, like example is boron is there. B2H6 is a very important compound of boron, hydrate of boron. It's very important. It has a very nice structure. Boron, two atoms of boron like this connected. Okay, and there are hydrogens all around it. Six hydrogens around the two boron atoms. Okay, then coming to the halides, the elements of group 13 form trihalides of the type MX3 because valency group oxidation state is +3. Okay, so examples only you try to remember the examples BF3, BCl3, BBr3, Bi3. Okay, rest is not required. Okay, then here reasoning is given. In the ground state electronic configuration of boron, you can see 1s2, 2s2. Then in the first hash state, this 2s electron is transferred to the 2p orbital. Okay, that way. And then finally, uh, the other electron is also sent. So the hybridization is happening over here is sp2 whenever it is combining with the halogens over here. Okay. Now formation, this formation of BX3, BCl3 or BF3 or BBr3 is shown over here. Okay. Then after that, I request you all to try to practice these Lewis structures: boron trifluoride, ammonia. Okay, boron trifluoride ammonia complex. Okay, it is an addition compound. Okay. Then if you look at the second column on this page, the Lewis acid strength of halides of boron follows this order. That means strong Lewis acid over here, this side. Okay, explanation is over here. It is not required. You can leave it out. Then coming to the next page, page 644, halides of aluminum. Only these structures you can have a look. Aluminum chloride, it is existing as a dimer, Al2Cl6. Okay, this one. You can go through. Then after that, oxides and hydroxides. Oxides, this reaction you try to learn. Reaction of aluminum chloride with ammonium hydroxide. Boron with oxygen to form boron oxide. Aluminum with oxygen from aluminum oxide in a similar manner. The equations particularly. Then character of oxides and hydroxides. The order I want you to remember, this order. The oxides of the elements of group 13, weakly acidic. If you move this way, the acidic character of oxide and hydroxide is decreasing, but basic character is increasing this way. Okay, so this order you try to remember in the case of oxides and hydroxide. Okay, reasoning not required. Then the equations over here: reaction of boron oxide with sodium hydroxide, hydroxide with sodium hydroxide with salt and water. Same thing with this also. Okay. And on page 645, reaction of aluminum hydroxide with an alkali and an acid to give salt and water. Important reaction. Now after that, solubility in water. This is noted to be noted down. Mark it over there. The hydroxide of boron, that is boron hydroxide, is soluble in water. But the hydroxides of aluminum and other heavy elements of the group are insoluble in water and form gelatinous precipitates. Now, why? The solubility of boron hydroxide in water is due to the Lewis acid character. It is behaving like a Lewis acid, okay, which can donate electrons to form this soluble compound over here. Okay. Now, as usual, as I've told in the previous classes, the first element of each group behaves anomaly, behaves quite differently. Now, here also in group 13, boron as an element over here, it shows anomalous behavior because of this reason: small size, high IP, high IEN electronegativity, and absence of backend d orbitals. So because of this anomalous behavior and because of these properties, uh, the various characteristics of the elements or the compound which boron forms, it shows the following differences over here. It's a metal, it's a non-metal, while the other members are metals. The melting and boiling points of boron are much higher than those of aluminum. Boron is a bad conductor of current density, while the other elements of the group are good conductors. Boron shows allotropy. and exists in two forms, crystalline and amorphous. The other members do not show allotropy. Then boron forms only covalent compounds, while the next member, that is aluminum, forms both covalent as well as ionic compounds. That's why you can talk about it being amphoteric in nature. Boron shows a maximum covalency of 4 in its compounds, BH4 minus. Okay. Aluminum, other members of the family can show a covalency of even 6. Boron forms a number of series of hydrides, which I've already seen, which are called boranes. B2H6 is a very good example. Inorganic benzene. The boranes are stable covalent compounds and are volatile in nature. The hydrides of aluminum and other elements of the group are non-volatile solids. They are less stable and decompose on heating. So you can underline this. The hydrides of aluminum and other elements of the group are non-volatile solids and they are less stable and easily decompose on heating. Then number 8, we will try highlights to leave it out. Coming to the second column over here. Number 9, the oxide and hydroxides of boron are weakly acidic. Remember this. While those of aluminum and other members of the group are either amphoteric or basic in nature. The oxide of boron, which is B2O3, boron oxide, is soluble in water, while the oxides of other elements are insoluble. Okay, so now after this general characteristics of boron, the anomalous behavior, we will discuss the diagonal relationship between boron and silicon. This element, boron and silicon, they are placed diagonally opposite in period 2 and period 3. Now, this diagonal relationship of these elements, it is basically because of the charge by radius ratio. The charge by radius ratio, it is almost similar. That is why they bear a diagonal relationship. Okay, so here boron belong to the second period is placed diagonally opposite to silicon belong to third period in the periodic table. Therefore, as expected, boron should exhibit a diagonal relationship with silicon. In fact, this is true. Boron resembles silicon in several properties in spite of the fact that the two belong to different groups as well as different periods. The diagonal relationship between boron and silicon is due to the following reasons. As I told you, the atomic radius is almost similar, not much of a difference over there. The radius of boron, 85 picometer, is close to that of silicon, almost 118 picometer. The two have almost similar values of electronegativity and ionization energies. So because of these two reasons, they show a diagonal relationship. Now, the important properties in which boron relates with silicon are given over here. Occurrence in nature. Both boron and silicon do not occur free in nature. They are always in the combined state. Non-metallic nature. Both boron and silicon are typically non-metals having high MP and high BP. Both are bad conductors of electricity. Allotropy. Both boron and silicon, you can see, dissolve, what you call allotropy, exist in two allotropic forms. So remember the allotropic forms. One is amorphous form, and another one is crystalline form. Then reaction with alkalis, they react with alkalis to give this borates and silicates and liberate hydrogen gas. They will combine with hydrogen to form similar hydrides, like boron with hydrogen it forms diboron, silicon with hydrogen it forms silane. Okay, tetraboron is possible, disilane is also possible. Formation of oxides, both boron and silicon form oxides when heated in oxygen. Their oxides and this one, boron oxide and silicon dioxide are having high melting points solids, and they are basically acidic in nature. They dissolve in alkalis to form borates and silicates respectively, as you can see in the equations over here. Borates and silicates. Formation of halides. Boron trichloride and silicon tetrachloride react with water to form boric acid, silicic acid, and then hydrochloric acid. Now, due to the liberation of hydrochloric acid, the chlorides fume in moist air. So, whenever you react these chlorides with water, they'll form the respective acid, and hydrogen chloride gas is formed, which fumes in moist air. Okay, so now after that, number 8, formation of binary compounds. So boron reacts with magnesium to form a binary compound, magnesium boride, and silicon also reacts with magnesium in the presence of heat, in the absence of air, to form magnesium silicate. Some of the borides and silicides undergo hydrolysis to yield boranes and silanes respectively. Go back. They undergo hydrolysis backwards and give back the respective boranes and silanes. Semiconducting nature. Both elements, boron and silicon, are behave as semiconductors. Okay. Now, after that, if you look at the next topic over here on your screen, that is boron, the first member of group 13. Now this study of boron, it's required. Okay, so here this part I will do in the next class because it is already time up. So I will stop my class here only. Okay, I'll stop my class here only. Today is 28th of October 2021. So tomorrow in the next class, in the sixth period at 12 o'clock in the afternoon, I will continue from boron. Okay, so with this I would like to end my class over here only, and in my next
Yes,
class
sir.
I will continue and try to proceed with this chapter. Okay, so just hang on over there because I need to record your attendance also. That's very, very important part. Okay, and I can see there are only 18 students present. Okay, so no problem. I will attendance. I'll record the attendance and then I will, you know, deal with the absent boys later on slowly. Okay. So with this, thank you so much. Have a nice day.